We're going to do another question on projectile motion now. We're going to look at a slightly more advanced topic where we're going to actually track the curve itself using the equations of motion. Let's just look for a second at a projectile motion problem. Okay, here we've got this. Now this is time over here. So let's pretend that time is the ground, okay, and this is delta x, which is the displacement from the place where I threw it. So as it goes up like that, the projectile has done that. If you've watched the flight of a golf ball or a lob of a tennis ball, you'll see that it generally goes, and they call it an arc, okay, but it goes in a particular shape. Now, essentially, we are throwing it up. Time is marching on, so this is what we are seeing. We're seeing the ball going up, and then it's doing this as time is marching on, right? Now, let us just consider the following, just for a second, okay? Let's consider, let me just move this up slightly while we remember that. Remember, we've got one of Newton's equations was delta x is equal to VIT plus a half AT squared. Now, for others of you, that is S is equal to UT plus a half AT squared. All right? Now, let's just rearrange this slightly. Delta x here, okay, is going to equal to a half AT squared plus VIT. And if we rearrange this, S is equal to a half AT squared plus UT. Now, can you see the similarity with this following format? Y is equal to AX squared plus BX. Y is equal to AX squared plus BX, where the coefficients, in fact, are a half A and VI, or a half A and U in this case, all right? Is the coefficients A and B. All I've done is I've just switched it around. That's all. Okay. So over here I can also say, just to bring in quickly, if you look, I have got plus 0 and plus 0. All right. Now we'll get to that plus 0 in a minute, which is essentially a y-intercept, isn't it, of a parabola. Let's now have a look at this displacement graph, shall we? Let us say that in this situation, right, the displacement up, this is positive in the upward direction. Okay. Now let's have a look at the other vectors applicable here. Well, first of all, I've got a velocity vector. So I've got velocity v initial is also positive. Why? It's positive because it's in the upward direction as well, isn't it? So my velocity initial is in the upward direction. My displacement is in the upward direction. What is pulling down? What is the down vector? Acceleration is negative, because acceleration is acting down and down, right? Now remember, in the conventional method that I've said, you split into up and down. Up, acceleration is negative. Down, acceleration is positive. That's just so that it makes it easier to process and split the two sections apart. It just avoids confusion, right, in solving the problem. This is if you want to do the problem all in one. Now, the next question is this one then. We say, all right. Now, therefore, let's just fill in some numbers here. All right. We can say that delta x, I'm going to keep using the delta x for the moment, but S equals UT squared plus a half AT, UT plus a half AT squared is equally applicable, as you know. Okay. Let's have a look here. Delta x is equal to a half times minus 9.8, because this is my gravity. Correct? There's my gravity plus v initial t. I'll just put a constant in over there at that point, just for the thingy of it. This is equal to minus 4.9 t squared plus v initial t and plus c. Now, in this situation, okay, let's go back and do a problem, right? Let us do a problem, shall we? Here we've got a projectile launched from the ground. So I'm just going to draw a graph here. We've launched it from the ground. It's going up like so. Okay. And remember, this is t and this is delta x here. So delta x is actually measuring the height of the projectile, isn't it? So we're going up and we've said that, let's say v initial is equal to 20 meters per second, or ms minus 1, all right? And therefore, let's have a look. Delta x is equal to minus 4.9 t squared plus 20 t plus c, which is 0 in this case, right? C is equal to 0. Let's just solve it conventionally first, okay? Remember what I said. Let's say take the upside on the up and the down. We said, right, up, okay, acceleration minus 9.8, v initial equal to plus 20, and we then said, let's just solve oh yes, and vf equals 0 at the top, remember? Those are what we put in straight away. Therefore, time to the top is going to be v final is equal to v initial plus at, which is going to be 0. That's my initial velocity. Sorry, my final velocity at the top is equal to 20 plus minus 9.8 t. Therefore, t comes out to be 2.04 seconds. And we then would say, right, at this point, this is 2.04 seconds. Immediately, you can say that's 4.08 seconds. Why? Similarity, whatchamacallit of a parabola, right? That side's equal to that side. The words just left my head right for the second. Okay, so now we say, all right, what about the how far? Well, yeah, let's have a look. How high did it go? Okay, let's have a look. How high did our parabola go? We said delta x is equal to v initial t plus a half a t squared, remember? V initial is 20 times 2.04 minus a half times 9.8 times 2.04 squared, correct? Therefore, that is going to be equal to 40.8 minus 20.4, which is equal to 20.4 meters up. Okay, now let's look at something slightly different, shall we? Let's use this formula here of delta, whoops, get it still, delta x equal to minus 4.9 t squared plus 20t plus 0, right? Let's solve for delta x equal to 20.4, okay? Right, therefore, let's have a look here now. Now what do we say? Okay, we say if delta x is equal to 20.4, I've just put in a distance. Now, note, why did I use 20.4? Essentially, I've said it's gone 20.4 meters up. So I am using this number here, aren't I? I'm using this one, 20.4 meters there. I've put in the height, which I've previously calculated, right? Let us now see and get what time. At what time does it reach that height? In other words, at what time does it reach the apex? Okay. Well, quite straightforward. What we can do here is we can do this. We say, right, delta x 20.4 is positive. Why? Because positive is the height up, isn't it? Okay. Positive up, vi up, a is acting down. So therefore we say 20.4 equals minus 4.9 t squared plus 20t. Now we solve for t. It's a quadratic. It's minus 4.9 t squared plus 20t minus 20.4 equals 0. This is A, this is B, and this is C. And if we bang that into our calculator, we are going to eventually end up with t equals to 2.08 seconds, or t or minus 2 seconds. And minus 2 seconds, not applicable because we don't go backwards in time. Okay? Now, let's examine the same. Can you see that the time it takes 2.08 seconds to get to the top? All right. If I put in, for example, when is delta x equal to 0? I would say 0 is equal to minus 4.9 t squared plus 20t, and therefore we could factorize that. Minus 4.9 t plus 20 equals 0. Therefore, t equals 0, or t is going to be equal to 20 over 4.9. Let's just quickly do that. Okay, t is equal to 20 divided by 4.9 is going to be equal to 4.08 seconds. 4.08 seconds, okay? So therefore, where are we? By the way, the 2.08s, the 2.04s, just check if you put it in as mode 5 and 3. I just want to check minus 4.9 equals 20 equals minus 20.4 equals you get 2.08 seconds, okay, there, and you also get minus 2 seconds, okay. There are slight rounding errors in this, all right, which you're going to see because that's the algorithm it uses, or it's just basically the way we're going to round it. Now, let's just move on and have a look at what is this. A lot of the problems that we're going to get, let's rather look at it that way, is we get problems where we have an initial elevation over here. We have an h, let's say 20 meters up, all right? And we're going to use the same problem, v initial equal to 20 meters per second. And this object is going to go up like that, and then it's going to go down and hit the deck over there, right? Now, essentially, it's a parabola with a given y-intercept. So that's equation of that parabola. The delta x of this parabola is going to be equal to minus 4.9 t squared plus 20t plus 20. Why? Because the displacement is up, it's positive. Let me just extend this backwards. Maybe that will also help, because can you see there? It's, you know, well, not really very good. Let's just make it a bit neater. Okay. Try and get it a little better. Okay. Can you see that it's essentially a parabola that's been cut off? This is the y-intercept over here, right? There's the y-intercept of a parabola going through, and that's the word I was looking for earlier, the axis of symmetry, right? So what have we got? We've now got a parabola that's doing that. If we now go and we say, okay, we know that that's that, okay, we know that the original one was 2.04. So we know t up here was 2.04 seconds, and therefore we know that t to down there was 2.04 seconds, all right? We know, therefore, right, what if delta x is equal to 0, all right? If delta x is equal to 0, we would solve that. If delta x is equal to if t is equal to 0, okay? If time is equal to 0, delta x is equal to plus 20. What are we saying? We're saying that here's our precipice and here's our ball that's going up, right? There, 20 meters, so it's going up and down like that. So at time 0, where am I? Okay? Hence, this is how you solve all the graph problems. Always look at the points of relevance. Where am I, or what am I doing at a specific time? So I say, right, I'm here. So at this point, my displacement is 0. Because I haven't moved. However, the displacement is relative to the ground. Therefore, I'm 20 meters above the ground. That's the critical part here, right? So cool. We say right. We're there. Now let's have a look and put in here, what is delta x if t is equal to 2.04? So we put delta x equal to minus 4.9 times 2.04 squared plus 20 times 2.04 plus 20. And the answer comes to be 40.4 meters. Why? Where's that? Well, it's here. Because originally when we threw it up, we were 20.4, remember? Now all I've done is I've lifted the whole starting position up. That's all we've done, okay? So the next step is to say, right then, let's calculate how long it's going to take to fall 40.4 meters, right? Let's say we start over here now. Let me just go back and let's put in red. We start here, V initial equals 0. And now I'm going to work out time to fall down, okay? I'm going to use the old way first, right? I'm going to say, okay. Whoops, let me just get back to my thing. I'm saying, okay, delta x. This is the old way, remember? Sorry, let me just put that there. Delta x is equal to ut plus a half at squared. Okay, v initial time plus a half at squared. Therefore, delta x, I said, was 40.4 equal to v initial was 20, correct? 0 times t in this case, plus a half times 9.8 times t squared. All right. If I solve for t, it comes to be 2.87 seconds, plus or minus 2.87 seconds. Therefore, what is my flight time? Flight time is time up, okay, which was 2.04, and down was 2.87. All right, which is going to be 4.91. So in other words, the time to go from the top here up and down was 4.91 seconds. 2.04 to the top, 2.04 to that point again, and another bit going down, right? Can you see that last 20 meters? It fell pretty fast, okay? Right, now, let's use our equation, shall we? The single equation for this. Let's use that guy, and we say, all right, delta x is equal to minus 4.9 t squared plus 20t plus 20. Now input 4.91. Let's say, where is the ball or the object after 4.91 seconds? So 4.9, whoops, sorry, my bad. 4.9, come on, 4.91 seconds. They've told me that, so I want delta x equal to minus 4.9 times 4.91 squared plus 20 times 4.91 plus 20. The answer that I get is minus 118.12, okay, plus 98.2 plus 20, and my answer is 0.08. All right? In other words, I've got a 0.08 rounding error. The actual thing is 0. What it's saying is that it's hit the deck at that point. Now, let's take it one step further. Okay? Let's take this equation here, delta x equal to minus 4.9 t squared plus 20t plus 20. Now I'm going to do dx by dt. I'm going to use calculus. The first derivative, all right? The first derivative is minus 9.8t. Why? It's because it's minus 4.9 times 2t to the 2 minus 1, right? Plus 20, right? is plus 20. Okay, because that becomes, the t goes to 1 times 20 and t minus 1. And what do? We put f prime equal to 0 to find the turning point. Minus 9.8t plus 20 equals 0. Therefore, at t equal to 2.04 seconds is when it is the turning point. All right. You could also use the turning point of x equal to minus b over 2a as well. Okay. That would also give it to you. So, yep, on any one of these, okay, we can use the full equation. Let's have a look here. Or delta x, let's have a look at this one. Okay, I've just done this. Delta x equals minus 4.9 t squared plus 20t plus 20. Okay, put delta x equal to 0. Okay, so 0 is equal to minus 4.9 t squared plus 20t plus 20. Remember that quadratic equation is the one that is in fact governing the entire motion, right? So if I put delta x equal to 0, it's saying find the time when the displacement is 0. Well, I say, okay, I get here, okay, delta x equal to 0, and it comes out to be t, okay, I'm going to solve t is equal to 4.91, or t equals minus 0.83. Okay, what does that mean? It means that at that point when delta x is 0, okay, the time is 4.91 seconds or minus 0.83. Let's just quickly go back to this piece here and examine what am I saying. Remember, this projectile was launched from a roof up there, like so, right? Okay, and this was the backward curve. This was t equals 0, it was plus 20 meters up. At t equals 4.91, it is on the ground. The displacement is 0. Because it is measured from here, not the top point anymore, right? So, therefore, we say that this must be minus 0.83 seconds on that side. In other words, it would have been on the ground 0.83 seconds ago. Yeah, it's a bit odd. Point is, you get a negative number, you just ignore it. Okay? That was the sort of the end of projectile motion and starting to move towards graphs of motion, which I'm going to do next. I'm going to recap the ticker timers, and I'm going to look at a few others. As I say, don't worry if you haven't done calculus yet. You will do it at some stage. That was just a little bit of a view as to another way of doing it. There's many ways to do it. The best way, projectile motion, split it into up and down. Okay. If you're very confident, you can use a single equation. It's not that difficult. Cheers. Have fun. In fact, you can try these yourself, You can time them from a height or whatever you like and see if you work out what the initial velocities are or whatever. Remember, you can be asked this different ways. They can give you total flight time, various other. All you do is you split it up and put in what you know. Start with the most information and then work backwards. Cheers. Have a great time. Bye.